subject of this lecture is a model of one-dimensional spin glass with oscillating long-range direction. Interaction is written in Fourier space on the left. So it is just example of what I mentioned in the morning as a nearly matrix in which spins are sitting is nearly spin density wave. So the Fourier transform of interaction has a strong peak at p equal to q. And kappa is the inverse range of interaction, which is very small compared to q. In one-dimensional space, interaction is just exponent multiplied by cosine. In three-dimensional, it would be this sine divided by x with exponent, but basically the same. And we will assume that concentration of spins is large compared to kappa, so on a typical range of interaction there are many spins. But at the same time, distance between neighboring spins is large. This condition C much less than Q means the typical distance A what we see is much longer than inverse Q, so wavelength of oscillations, which makes all these couplings completely right. Hamiltonian is written here, H, and there is external, in principle, external field H. Let me mention also that in one-dimensional system, if this random interaction will be nearest neighbor interaction, which would be the case if I would have one of the C larger than one of the kappa. I have actually the opposite condition. But if I would have this condition, the system would be trivial because although side of each coupling would be random plus or minus, but it would be no frustration. You always could simply redefine spins in such a way that, say, sum of sigma I would redefine to tau I minus sigma I in such a way that interaction between these tau spins would be ferromagnetic. So up to the redefinition it would be trivial situation. But when we have multiple interaction due to long range interaction, there is no way to make such a thing. So this model was invented at the Mikhail in this post-paper of 83, and then developed to some extent. Development is in the review book published in 1990. So now some theoretical machinery. First of all, we decouple interaction between spins. Here we'll get all this on the web, so there is no need. We decouple this interaction via some Hubbard-Stratonovich auxiliary fields. This field should be complex, psi and psi dagger, because there are oscillations.
random? Okay, thank
They
you.
are absolutely random with a given concentration.
Okay, thank you.
So, this is a exact transformation on the first line. If you integrate over sine psi tag, you are back to this partition function with the Hamiltonian rate. But now we can take a trace over all these sigma I variables because they are decoupled. The result is here. It is sum over points where spins are sitting, and with this logarithm of hyperbolic cosine of effective field, psi plus y plus tau. And we will work with this representation. First of all, we consider critical point. Of course, there is no real phase transition in one-dimensional system, but it is nearly phase transition under the condition of long range of interaction. So when I will talk about this critical point, actually I would mean that it is almost thermodynamics, not exactly. So we neglected the most long time process. I will specify which one. To look for the transition point, as usual, we expand over this psi, like it is done in Ginzburg-Landau theory of phase transitions. So, first term with psi squared gives you something random multiplied by psi squared, but average of this random is just this tau 1 minus c over t. And then there are some other terms in the last line.
C is concentration.
C is concentration, yes. At t below Tc, which is equal to concentration in these units, average value of a coefficient in front of psi squared is negative. So it seems there should be some other parameter. My condition of not complete but nearly thermodynamic approach means before. All time scales are less than is exponentially large, 1. By the way, gamma here, you see, this is important small parameter of the problem. It just tells us that inside the range of interaction there are many speeds. So it is usual Winfield-like condition. So as long as time scales are less than this Tm, we can neglect some phase slips which should actually bring us back to high temperature phase in absolute equal time to infinity. Now, we see in this gradient term, it is not just derivative, but derivative with q. So we expect that for the parameter should have a wave modulation, the wave vector cube. So reasonable order parameter looks like this. Psi is some amplitude and exponent of iqx, and also some additional phase phi, which is a slow phase gradient. We will be working with the functional of this slow phase. minimize this free energy over amplitude of those values, rho. Then this minimization condition is shown here with number 7. It is given by here there is a random phase alpha. Alpha is basically the same as alpha is at each point is q x I plus phi I, and this is basically random. So my self-consistency equation is shown here. I should average over random phase alpha here. It will give me equation for and infield free energy written below its equation. This is not more difficult than usual Landau equation for ferromagnet. So free energy as function of rho is written in equation number 9, and the term which depends on magnetic field is also contained with rho squared and just h squared second third term. So from this free energy, you can easily get simple results, like for specific heat and magnetic susceptibility. For example, for susceptibility, T would get 1 over C over T behavior here, and at this point, just cast which corresponds to yes, with 1 minus modulus tau.
So,
Yes.
in the average of sigma I, we have not in the cosine the field anymore. So there is no. Why there is no the field anymore? Because there is no frustration in this sense.
You will see there is average this sigma I average is given by this formula. The x is random coordinate, so it gives you oscillations. And also there is a phase variable phi. In the simplest approximation, you would think that this phi is just some constant. But in fact, you will see that variation, that this equation has a very large number of solutions, which exist due to different metastable states. And these different solutions are enumerated by different distribution of phase. This is our major point, which I will come in a moment. So, from this moment, I'm going to consider non-trivial part of the story, namely free energy, which depends on a phase variable phi, and the effective Hamiltonian in terms of this phi is written on the left, on the upper line, because I had two variables, amplitude rho and phase phi. I already made minimization of rho and take this rho corresponding to minimum. Now I'm left with this phase. Energy as function of phase contains first term, which is a gradient, and second term, which is the sum of this cosine 2qx plus 5. Formally, this is just the same Hamiltonian as is known in the theory of charge density waves or spin density waves. There you have some density wave modulation in a solid, and the variation of phase in the case of this charge density wave means just the shift of this phase by some distance. Phase is like a common coordinate of this density wave. And the cosine term corresponds to impurities. If there are impurities in this solid, they interact with density wave, and then it depends on the specific phase of this modulation. So, like density delta rho is proportional to cosine x plus phi. These are some random phases, but phi is a dynamic variable, and you need to always to find some minimum extrema of free energy is functional of this phase. Is it clear at the moment? Now, how to deal with this problem? Of course, you can write down you can take a variational derivative of this h phi, and you will get simple equations like phi second derivative equal to some sum here. Take a function cosine phi plus will be this kind of equation. You even could try to simulate it. It looks simple. But it makes absolutely no sense to simulate it because solution of this equation, if you consider it as a problem with initial conditions, so the second order differential equation, you can choose phase at the phi of 0, phi prime of 0, you choose them, you start to solve, and you get nonsense, which has nothing to do with physical solution, because this equation is solution of such equation is chaotic. A small variation of initial conditions leads to completely different solution, sufficiently viable outside beginning. So most of solutions which you will get this way would have very high energy and have nothing to do with real physics close to equilibrium. In order to avoid this problem, you need to consider a different approach to, in a sense, to classical mechanics. The equation which I just erased could be considered as Newton equation, second derivative. Instead of considering this type of equation, we can switch to Hamiltonian equation. In this problem, it means the following. Let us consider something like a partition function corresponding to this psi n, which depends on phase at point n. We consider it as a partition function of our system, which contains of many spins. And we integrate it over all but one phase. This is why it is a function of phi n. Now, because in this representation, the energy is already local, we can add one more point to our system. It was n points, now it will be n plus 1.
Mhm.
And we can write down the transfer matrix equation for partition function. It is not written just for psi, but what is written here is an equivalent equation for logarithm of psi. Epsilon n and epsilon n plus 1 as function of phase is nothing but conditional free energy of a system, conditioned by the value of phase at the last point of the chain. And this is exact recursion relation. What happens with our function epsilon of phi after I add one more point to the system? Do you understand the idea?
No, I don't.
Okay. So
So you're adding one impurity, one,
yes.
yes. Mm-hmm.
Recursion equation for partition function.
Mm-hmm.
Here I integrate over phase phi n, which was originally phi last point, but now it is not last, but because last is phi n
N
plus
plus one.
I assume that this is the last major term, because remember gamma is small parameter.
Uh-huh.
So I take Gaussian integral over phi n,
Mm-hmm.
and also I write z, which was psi there,
Mm-hmm.
in the exponential form.
Okay,
So instead of z, I use this epsilon.
okay.
After this simple operation, I will get this equation.
Okay.
Now,
So are we discretizing space to write the derivative of
it
phi?
is discretized because our spins are sitting in some random points, and we
Okay,
just
so
go
it's
from
just
one
like
to
this
another.
notation of, okay.
Just from one to another. The distance, of course, is random. It is sitting here.
Mm-hmm.
So this L is also a random quantity, but this is not very important.
Okay.
low temperatures, we can even neglect this term with second derivative. Then it would be exactly discretized Hamilton-Jacobi equation, corresponding to this dynamic equation. And now our goal is to study properties of this function epsilon phi. This will be our major object. Because epsilon of phi gives us a potential relief for our problem. We can change phi and look how many minima it has on a period of 2 pi. We will see that as long as we go to lower temperatures, the number of this minima will increase and increase. But in this form, with this simple cosine function, it corresponds to relatively high temperature, not very far from our approximate TC. Here, we can use some simple analysis. For example, it was developed for actually for this charge density wave P problem. And for example, we can consider try to use parameterization of this function as just a simple one harmonic in terms of x. Then our first goal is to estimate what is the typical value of this coefficient. That can be done, and I will show how it is done. There is some typical scale of this. To somewhat more details how we operate with this stochastic transfer matrix. Let us first try to use some Taylor type expansion. Suppose there is a minimum of this function at some point gamma, and we expand in power series. Of course, the gamma itself is a random. When we move from point n to point n plus 1, it will shift. How much it will shift? It shows we need to find minimum, to relate minimum point at for n spins with n plus 1 spins. Here we get this simple relation. The beta is a second derivative in the point of view.
Sorry, gamma is what? Again?
Gamma here, it is a point corresponding to a minimum of epsilon
Okay.
n as function of phi.
Okay. So you're finding a recursion relation
Yes.
for the point of minima.
Yes, for point of minimum and for
Why there is
second
only
derivative.
one? Why there is only one minimum for each n?
It might be more, but I just find one minimum
Okay,
for phi n.
and then you propagate it.
And then I propagate. I add the next spin. I get a new function epsilon with differences here.
So essentially, the idea is you take your charge, your density wave, you pin it by one spin, which is easy, right?
No, it's not that I pin it. I pin it in the sense that I choose the phase,
You choose the
magnitude
phase
of the last spin.
to lock it
Integrate
on.
over all previous ones.
So let's say you have one. So you choose the phase to pin it on this first spin. Then this condition gives you what is the position of the next minimum.
Have a minimum for next spin.
I mean, if you put two spins, where the position of the next, of the minimum for two spins will be, and so on and so
Yes.
far.
Yes.
Okay, so that's how.
Yes. This is a recursion written here in terms of position of a space gamma and for how much the second derivative in the point of minimum changes. This beta is a curvature of my
And the random quantity is xn.
Yes. This qxn is a random quantity. I will, because it is typically a large number which is absolutely uncorrelated with up to 2 pi.
And you need to do this construction simply because the spacing between the xn's is random
Yes.
and is not equal to the inverse of
Yes.
the momentum of your wave.
Yes. Yes. It is random, incommensurate random.
Yeah, okay.
So this is
Ma chiedi devo spiegare. Misha, I guess some people are lost, so.
so you need to ask me.
Yeah, but they are not used to this kind of interaction we're having, so.
Let's
I'm trying to engage them,
Yes. Yes. That's right.
right? So,
Yes. Right.
let me try to explain it in simple words and maybe they will ask questions. So, the problem is you have a you have a density wave that has a momentum, that has a lambda, a wavelength lambda. So if the impurities would be spaced with the same wavelength, the problem of pinning the wave would be trivial, right? But the problem is that they are incommensurate, they are randomly spaced. So if you put one impurity, you know how to pin the wave. You just put it in such a way as to minimize the interaction. If you put two impurities and the spacing is random, well, you have to find every time the new minimum, which is not guaranteed that is going to be a nice spacing, and so on and so forth. You increase the number of impurities, and you have to find iteratively the new minimum. And that's what he's doing, okay? As far as I understand.
Right.
Am I right?
Absolutely right.
Okay. So he's writing a recursion relation to find the minimum of the position of the density wave such
I think
that.
you know from statistical mechanics course what is transfer matrix
Yeah.
approach, right? Here the trick is that because system is random, we cannot write down simple eigenvalue equation for transfer matrix, but we need to treat this transfer matrix as a random quantity itself. So it is not eigenvalue problem, but it is a dynamical problem for the transfer matrix. And it is more convenient to use not a partition function but its logarithm, which is effective free energy. This is what I am doing. Recursion equation for free energy as function of a phase of velocity. If I want to write down recursion for the curvature of my effective patterns, then it is here. It is not closed in the sense that if you extract equation for second derivative from this general equation, you will get a term which contains derivative, fourth derivative. But let's try to make some estimate. If we are in some stationary state, then average of the left hand side should be 0. On the right hand side, we have average of beta squared, average of one of the beta with coefficient. And this term there is beta, next beta 4, and this one. Let us make an assumption that all these even beta with even numbers are of the same order of magnitude.
Why?
Assumption. With this assumption, we immediately see what is the basic scale of this small. The scale of a function is much larger. It is b small number v in power 2 thirds. So it is parametrically large. It means that the energy of epsilon, it contains contribution from many spins, many points. Each of them gives some relatively small contribution. Altogether, they give this amplitude of this free energy profile, epsilon of t. If we trust this estimate, let's look what happens now in one asymptotic region. Suppose we want to find probability distribution with W of beta is a probability distribution density. Probability to find beta large compared to this typical scale. Here at large beta, the equation is simplified. It is just this. It can be easily solved. Exponent of beta minus beta in power 3. And this is just statistics of shocks and Wilkes because it is described by the same equation. Now, let's look for another limit, small beta. What is the probability to find a point where my second derivative is small, so it is easy to move that stimulator. Here, expansion in terms of in power law, Taylor expansion is not useful at all. But instead, we can use Fourier expansion. We can expand this function in harmonics, and at small beta, high harmonics can be even neglected. Then you have another simple equation. It has actually two possible solutions. One is simply W proportional to beta, and another is beta below. Both are solutions of this equation. To choose between them, you need to take into account next harmonic and to look for stability. So stability analysis tells you that the actual solution is this. But now that was still some kind of introduction. Now we go to really interesting things. We go to lower temperature, and here our random potential V, which was cosine during some time. It is not just cosine. It is a logarithm of the hyperbolic cosine of the cosine. When temperature is low, this function is nearly like this, with a cusp. Near, apart from the region where this 5 plus qx is close to pi over 2, some 0 of cosine. And this is important. Our effective pinning potential is singular, at least singular in the sense that its second derivative is nearly delta function. It will make all our story very happy. First of all, what we need is to study a probability distribution for functions of this epsilon phi. Epsilon phi is a function, it is random, and what I want to consider a probability function defined on this function.
Mm-hmm.
To do it, I'm using a method proposed by Martin, C.G. and Rosen for classical dynamics with random noise. So here you see a probability generating functional in terms of some external sources, J. If J is zero, all this functional integral is just one, because it is constructed in a way that I write down the delta function of equation and then average. So first I exponentiate this delta function using integration over auxiliary mu. And then I should integrate over my fields epsilon and sources J I needed to generate some correlation functions of this epsilon.
Mm-hmm.
Is this trick known?
Kind of, yes. I mean,
Good.
to me.
Yes,
know
but what about
others.
students? If anyone does not know, please ask question. I will explain. Well, okay. Now, as I mentioned, our potential is singular, is zero. Let's make this singularity more explicit. In the potential itself, it is a custom.
Mm-hmm.
I want to change variables in such a way that instead of cusp, I will have a little function peak. So instead of integrating over mu, I pass the integration over some m large, such that its second derivative over phi is mu.
Mm.
Now this is our functional, and due to this trick, what we get is that here it is m instead of mu, and second derivative here.
Where is the Jacobian?
Jacobian is equal to 1. For this equation it is 1.
Okay.
So here it is second derivative, and in the bracket you see this v. Second derivative acts on a v,
Mm-hmm.
and it gives you delta function. Now we still need to average over alpha. It was here, it was alpha. After we got to delta function, it is easy. Direction. It is easy to average. We have this term, and from this potential, it is in the action, we have logarithm of this integration of phi, exponent, and m of phi. Now, let us expand over.
This is already the result of the average.
I
This is already, it is already the result of the average. Yeah.
result of average over alpha.
Wow.
Yes. This result formally is written in this term with logarithm of this integral.
Mm-hmm.
This is complicated object, but let us try to expand exponent over powers of m. First term, non-vanishing term, will be integral of m squared.
Mm-hmm.
Of course, there will be some higher order terms, but I will be able to show that these other terms are small in comparison to the quadratic. let's first neglect it at all. Then, remember, we need to integrate over L large. But if we throw away all this, integration is trivial, it is Gaussian integral. We are left with the action of this form. It is an action in terms of function epsilon. Epsilon is a function of phi and x.
Mm-hmm. Yeah.
So first derivative of x, second this derivative over phi squared, and all that. Now again I want to make a relatively simple dimensional analysis. Namely, suppose I have a fluctuation of this epsilon. It is a free energy. Suppose I have a fluctuation of this epsilon with a typical variation delta phi. I will denote it as phi large. And also this some kind of wave in this function. And also it has a special scale x. Imagine waves,
Mm-hmm.
many waves like on a sea. They have different scales in terms of change of phase, and also we have different locations.
Mm-hmm.
In terms of locations, with special scales. Now I want to relate three things. The scale of variation of phase,
Mm-hmm.
special scale, and the magnitude of this variation. Delta epsilon, which I will call E.
Okay.
Then I say, in this section, first of all, for typical fluctuations, this action is of order 1. It stays in the exponent. So for typical fluctuations, it is of order 1. And both terms here should be of the same order of magnitude.
Okay.
It gives me these two equations.
I mean, typically, you mean the most probable fluctuations.
Yes. From these two equations, I come to the relation between special scale and phase scale,
Mm-hmm.
and energy in terms of this
Mm-hmm.
phase.
Yes.
These are power laws. The larger is phase variation, the larger is special scale, grows as phase and power 1/3.
Mm-hmm.
And energy also grows like this, power 5/4. Now, neglected terms. What we can do is to demonstrate using this estimate that higher order terms are small in this parameter.
Mm-hmm.
I assume that t is larger than kappa.
Yeah.
So, good. Now, this estimate.
Misha, can I ask you something? But
Yes.
you know, in this one, now you're estimating. I mean, you're essentially studying the partition function of this
Mhm.
problem. But what do you? I mean, in order to determine glassiness, non-glassiness, whatever of this problem, what is the observable you want to study? Because I mean, the reason I'm asking is that here you're studying typical fluctuations. But if you have an observable from which typical fluctuations give us then maybe you should study an instanton solution, right? So,
Yes, there are, we will come to observables. Main observables which I will discuss here is just time dependent correlation function,
okay.
or an imaginary part of susceptibility.
So can you anticipate that typical fluctuations will be enough?
In this regime, moderately low temperatures, it is enough. Well, at least I think it is.
Mhm.
But the point is that this typical is a function of scale. It is not just a number, as you see here.
Yeah, yeah.
So there is something like inertial scale in turbulence.
Mm-hmm.
You may have different scales of your waves and the relation between energy and the scale. And this, in the case of application to the spin glass, it will lead very soon, surprisingly, to a hierarchical structure of minima. Although we don't have anything like Paris scale.
Already at this level? Already for this one? Oh, okay.
So, what is important here? This scaling, like shown here, it works if in between some limits. Of course, for phase, the natural limit is just 1 or maybe pi, the upper limit. But there is also a lower limit, minimal pi, which is proportional to temperature.
Mm-hmm.
Why it is proportional to temperature? We remember we replaced second derivative of our complicated pinning potential by delta function. But actually it was not exactly delta function, it was delta function smeared on the scale which is determined by t. Remember. So the lower is t, the more sharp is this delta function, but still there is a smearing. And this smearing defines the lowest scale in terms of phase, until which this scaling analysis is based. Now, one of the observables is a phase correlation length, namely let us find a length such that when we move along this length, our phase shifted by the amount of order 1.
Mm-hmm.
The condition is here, because delta phi is random. It is with diffusive growth, and each delta phi is expressed, delta phi scales as 1 over beta, beta is second derivative of my function, and because function scales like this, the scale of function grows with phi. The scale of first derivative also grows like phi in power 2/5. But second derivative already has a negative power. So the magnitude of the second derivative is determined by smaller scale. So that allows me to estimate this second derivative and finally come to the result for phase correlation length, which grows with decrease of temperature. Now the most interesting part of the story. This scaling, as I will show you now, implies that when we decrease temperature, number of different minima of my function epsilon grows with decrease of temperature. And moreover, they grow not in an arbitrary way, but they grow like it is grown here. That new, as long as we decrease temperature, new minimum grow up from the vicinity of previous minimum. Like it is shown here.
How can you say this?
I understand that quantitatively.
Yes. Look, consider a function. Suppose this phi1 is one of the mean. Consider a function f, which is first derivative of energy, so just a force. And ask the question, what is the probability to find f is 0 after a shift by some amount? So we have one minimum, but we want to find another. Suppose we shift by this phi large. A characteristic scale of this thing is what we know as f of phi, which scales like this. Characteristic scale. On the other hand, the curvature of our function is determined by smallest scales available in the problem, which is phi naught. So probability to find another minimum scales in this form. It goes like this. Now let us estimate the total number of minimum which we can find. We need to integrate this probability over phi. This is normalization. Integrate from minimum phi naught to pi. Integrate this function and we get this. Phi naught proportional to temperature. So the number of minima scales as t to the power minus 1. All that may look rather contagious, and actually it was contagious.
Can it be checked numerically?
Yes.
Okay.
Relatively recently, I proposed to one bachelor student to study this thing numerically. This is what he found. These two plots are for different ranges of temperature, moderately low, very low. It is bachelor diploma, so it was not long story. But he found something which is not 1/3, but you see, not far.
But wait, so he took those equations epsilon n plus 1 minus epsilon n blah blah blah, and he solved it. That's what he did, numerically.
Yes.
Okay.
And counted number of minima depending on
And he did so for many realizations
Yes.
of this order, and then he took an average.
Yes.
Okay.
After this bachelor diploma, he left somewhere to industry. I never saw him afterwards. But I mean, this problem certainly can be done in a more accurate way. But even this first trial shows that we are not so far with this estimates.
May I ask a question?
Yes.
If I understood well, the picture with the hierarchical structure you showed is a graphical representation of the recursion formula you wrote before, right?
Which formula?
Epsilon n plus 1 as a function of epsilon n, let's say, of delta recursion.
It is not, this recursion formula is rather general. It leads to this kind of hierarchical minima under the condition that we're at relatively low temperature, and so our random potential is singular.
Okay.
It develops this kind of hierarchical structure because we have sharp
Okay.
features in the second derivative of our potential.
Okay. Okay. What I wanted to ask is that can you infer from that equation the number of branching at each step of the mean?
What we can estimate is the special scale corresponding to each of such fluctuations, like this x.
Okay.
So, of course, if you have very long system, you definitely will have independent minima at in some distant part. So, if you say this fluctuation of energy is of such scale x, then you may expect that if you just split your system into pieces of this size, the whole length is divided by this x.
Okay.
And it gives you a number of such fluctuations.
Okay. 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 Thanks.
So Misha, these two phases that you studied, the first one, and then this one with the cast potential, so do they correspond to different physical?
No, it is just different temperature regions.
Yeah.
One is continued to, there is a crossover from one to another.
It's a crossover.
Yes,
So there is no transition.
No transition, it is just continuous crossover.
Okay.
In close to mean field transition point, you have simple cosine potential and there is only one minima on a period, or maybe two occasionally. And when you cool down, number of minima grows. And grows like this power t in power minus 100.
And there is no thermodynamic transition whatsoever.
No. Now, observables. Different types of observables shows you some that different results. Of course, fully equilibrium susceptibility is trivial. It is just paramagnetic because in full equilibrium you don't have any phase transition in this one-dimensional system. But this is not very interesting. If you consider quasi-equilibrium there within this mean field approach, then you will get this field-cooled magnetization, which is just frozen at the level of 1/2. Also not very interesting. What is more interesting is dependence on time or a frequency at intermediate time scales, which can be very much different, T0 and T1, because this gamma is small parameter and here it is a negative power, and in T0 it is, gamma is in the same power, but temperature. Here it is one of the temperature, and there it is temperature and power different. So, average value of spin at some point at low temperatures is basically this. This cosine of phase, this is random, and phi is a dynamic variable, but its dynamics is slow because in order to change this phi, we need to cross some energy barriers, and we estimated this, the magnitude of these barriers. spin susceptibility, dissipative part, which contains a usual Debye factor,
Mm-hmm.
omega. Tau is a time needed to cross a barrier of a height E. Delta is a energy difference between these two minimums, so something like this. This is E and this is delta.
Mm-hmm.
And to get a final result, we need to average over both E and delta. This is the inverse just cosine,
Mm-hmm.
hyperbolic cosine square. And then R of E and delta is a joint probability density to find a barrier E and asymmetry there. Finally, N of E is the number of spins which flip during each such a move. So we move by phase phi, part of our chain of length x. So this is the total number of spins which are moved. So to calculate finally this imaginary part of susceptibility, we need to know this joint probability density R, because F, this function we already discussed. So L is a function of energy, is energy in power 4 over 5. M also is a function of power of energy. And what is R?
Where is that?
Integration over this asymmetry parameter delta is done in the following way. Delta scales of delta and E are the same. So, I mean, this function is smooth on the scale of E. And then it contains this sharp function inverse cosine. So this integration gives me simply extra power of t divided by n. Then I combine all these together and find imaginary part of susceptibility, which is a logarithmic function of frequency. Like in some examples which I have shown you on the first lecture.
Mm.
Very slow logarithmic section.
So wait a second, logarithmic, what does it mean in time domain?
In
In the time domain?
time domain, this correlation function
There
is
it is.
this. And this is correlation function. For response function, phi of t is proportional to derivative. Time derivative is due to fluctuation dissipation relation.
But this is seen somewhere in experiments, a logarithm? No.
Well, yes, it is C. Logarithm, inverse logarithm, logarithm with some power, or maybe power, power time like power minus 0.1. It is difficult to distinguish from what.
Okay. But the log, where does it come from here? From the one where No, it's not from the 1/8. It's from the combination of.
All combination, all these
Of the
things
W that goes like 1/8 to the 7 fifths.
yes, and these.
N of E that goes like e to the 4 fifths.
uh,
Tau of E that goes like, it's not written.
N of E is.
No, tau
here.
of E, tau of
It
E.
is written in terms of E.
Okay, so
Yes.
the combination of all those things gives you that
Yes.
law.
The combination gives you logarithm of frequency in power -3/5.
This is quite exotic. I've never seen such thing.
Look, this model is so simple. Classical chain of Ising spins.
Mhm.
Now you can easily simulate it on Monte Carlo
Yes,
and get all kinds of correlation functions.
yes.
We could not do it 40 years ago.
And how is the comparison with this solution of the Monte Carlo?
I don't know.
Oh, nobody did.
Nobody did it. I mean,
Nobody did.
the only thing which was done was this analysis of number of minima by the special student.
So, but let us recap what you did in this thing.
Yes,
So just,
yes.
okay, what did we learn? Okay, fantastic. So that's what we take home. Can be described by slow phase variable. Correct.
Yes.
But then you treated that as in a sort of mean fieldish way, no?
Yeah, it was, I mean, fieldish in terms of taking extrema of the amplitude of this
Yes.
space. And this was trivial. Non-trivial part is the presence of many solutions in terms of distribution of phase.
Yes, absolutely.
Each of these solution in terms of phase corresponds to different arrangement of spins up and down, up and down.
Mm-hmm. Yeah.
And the nice feature of this model is that if you look on spins themselves, sitting in random places and pointing up or down,
Mm-hmm.
you have no idea why this configuration turns to some this configuration. But when you look for the functional in terms of phase, you know that difference is that you shift the space by some amount.
But were you inspired, for example, by the problem of pinning of a charge density wave?
Yes, yes. Well, this is this problem I solved a little bit before.
Okay, so it's good to know.
Yes. It was a couple of papers of the spinning of charge density wave in 1980, 1991.
And the statistical mechanics is similar.
Yes, yes. This is
Okay.
what we just developed this approach of stochastic transfer matrix, which was used for charge density wave originally.
Mm-hmm.
But then we used it for this more complicated problem.
So in practice, we can think of using this method every time we have a wave that is pinned by a random potential
Yes,
in one dimension.
yes, yes.
So that can be it a charge density wave or these phase fluctuations or whatever you want. So the analysis will be similar.
Yes.
Okay.
So this free energy relief contains many metastable states with a tree structure
Mm-hmm.
that more small scale minima and maxima grows up from the
Mm-hmm.
broader minima. And this structure becomes more and more developed with decrease of temperature. Here, on one hand, there is evidently hierarchical structure of states. On the other hand, it comes from completely different, apparently, reasons in comparison with infinite range spin glasses and Parisi replica similar breaking
Mhm.
theory, which we also will discuss. Finally, I mentioned on the first lecture that it was a big and long dispute between two schools. If there is a hierarchical dynamics in spin glasses or a parallel dynamics in spin glasses.
Can you define what is parallel dynamics?
Parallel, imagine that you have many clusters of different sizes and different energy vectors.
Mm-hmm.
Smaller, larger, very large. So you have a broad distribution of relaxation rates.
Mm-hmm.
You can, by some assumption about probability distribution of these vectors, you can explain, so-called explain, any kind of slow relaxation.
Mm-hmm.
Relaxation of each of these objects is simple exponential, but it is exponential power minus
Oh,
u
it's like generating 1 over f noise out of
Yes.
Poisson processes.
For example, yes. So you have the gamma is a rate.
Mm-hmm.
Then you have distribution function of this gamma.
Mm-hmm.
And if it is, for example, 1 over gamma, you will get 1 over f noise, you will get logarithmic relaxation, and so any other relaxation, whatever you want.
Yes.
This is an idea of independent dynamics of various objects,
Yes.
and only the probability distribution tells you.
Okay.
Now, completely different picture is the following, that your microscopic states are arranged in a kind of tree-like picture. This is one state, another. In order to come from one state, for example, from this to this, you need to come two steps of hierarchy, and one go here. And to go here, it is many steps, 4 steps. So there is some, in other terms, what it is called ultrametric
Yes.
geometry of states, which has nothing to do with independent parallel dynamics.
Mm-hmm.
It is completely different type of thing. So the discussion was which type of dynamics is closer to real three-dimensional spin glass. Now looking on our simple one-dimensional model, what we can say? On one, we can say that it contains both features, both parallel and hierarchy. Because on one side, if I have very long chain, and I consider what's going on in near of its left end and near its right end, they don't communicate.
Mm-hmm.
What happens here and there is independent. On the other hand, there is some relatively long but finite range of distance. There, all my results for this fractal minima are valid. And here, within this range, I have really hierarchical organization of B.
So for the infinite range Sherrington Kirkpatrick, it's only hierarchical.
Yes.
Because you cannot think of a space structure.
Yes, because there is no space structure. But for finite range system, I think there is a mixture. There is a locality in the whole infinite system. Of course, there are some regions which are very far apart. We don't know anything about each other.
Mm-hmm.
But on the other hand, large part of observable dynamics is described characterized by hierarchical features. And at one of later lectures, I will even tell you about a very interesting experiment, real experiment, which was specifically designed to distinguish between two types of entities.
I see.
That was done in Urbana-Champaign 35 years ago.
Are you going to give us an exercise or not?
Oh, yes.
Oh, yeah,
Yes.
yeah. Let me take a picture.
So, look, I did not say it explicitly during the lecture, but my function, epsilon, which was, I discussed this recursion relation for this function. It was a function for half of the system. It is a function of a phase at the end point, but after I make addition of many spins. But if I'm looking on a whole system now, if I consider what happens inside, I should consider the phase inside, which and the energy is a sum of two functions of the same type, which comes from left and from right. This is actual quantity which I need to consider, because if I would consider thermodynamic properties only, then I don't need it. I can do equilibrium thermodynamics can be done just by moving along one direction, and I get this partition function. But I want to discuss dynamic properties, which happens inside the system. So, what actually I should analyze in space. And the question?
The question is, what happens in periodic boundary conditions? If I consider a chain in periodic condition, can I do this in analogous study by fixing a spin and considering the last half of the chain and do the same calculations, or it's very different?
Well, I don't know. It is the periodic directly it is not applicable. Probably you need to consider parts. I mean, at least two parts of the system, then try to merge them. But this is something a bit like what I proposed here, to consider this sum of these two random functions and to check if statistics of this resulting epsilon is the same as what I found for these two parts.
Oh, there's another one.
There are 5 of them. For you know that you have broad choice.
We will make it.
This is about this imaginary part of response and how to account correctly for not complete equilibrium. Because formula which I was shown assumed gives a distribution. It's because this one of the cosine hyperbolic square was used. But in a non-completely equilibrium state, it could be something else.
Okay.
with scaling of number of minima, with temperature, which I already discussed. One interesting computation would be to check ultrametricity of different configurations, because the presence of hierarchical structure means a specific relation of between distances between different configurations. Distance by distance, I mean number of spins which are different.
So you're saying you would get it by Monte Carlo simply because you would get trapped into one of them or the other.
Yes, but even so, you can find some minimum. Then you can find some another, second
Mhm.
and third.
Yes.
If there is a tree-like structure, then each triangle has two identical lengths
Yeah,
in hierarchical geometry.
you should compute the Hamming distance.
Hamming
of the
distance.
configuration.
Yes, having distance and to check if indeed it corresponds to this ultrametric structure. Well, number 4 is roughly what this guy did already. And number 5 is a quantum generalization of this problem. We can expect that non-zero quantum fluctuations will somehow smear this fractal structure at some temperature. Because apart from usually activation process, we will have some tunnels process. But how exactly it will happen, it was not yet found.
Mhm. Well, thank you.
That's it.
In the next 2 weeks, we will enjoy ourselves.
Good.
Okay, Misha, what is the next lecture, just to anticipate?
Next lecture. Let me check.
Which is going to be in